Hello there, and welcome to the Sleepy Science Place. I'm so glad you found your way here tonight. Maybe you've had a long day filled with decisions and noise, or maybe you're just the kind of person who finds comfort in the strange and beautiful mysteries that live at the edge of what we can know. Either way, you're exactly where you need to be. Tonight, we're going to drift together through the quantum realm, that peculiar layer of reality where particles dance in and out of existence, where light behaves like both wave and particle, where the very act of looking at something changes what it is. But don't worry, you don't need to understand it all. In fact, the quantum world seems almost designed to resist our complete understanding, and there's something deeply peaceful about that. You can let go of the need to grasp every detail. Just let these ideas wash over you like moonlight through water, soft and shimmering and strange. Before we begin our journey into the infinitely small, I want to invite you to get comfortable. Adjust your pillow, let your shoulders drop away from your ears, and take a slow breath in through your nose. Hold it gently for a moment, then release it like you're letting go of the entire day. Beautiful. If you're enjoying this kind of content, if these sleepy science journeys help you find rest, consider subscribing to the channel and leaving a like. It helps others who need this peaceful space find their way here too. But there's no pressure, no rush. Tonight is about you, about rest, about letting your mind wander through landscapes stranger than any dream. The quantum world is where reality becomes poetry. It's where electrons exist in clouds of probability until someone asks where they are. It's where particles separated by galaxies somehow know what the other is doing. It's where the universe reveals itself to be far more mysterious, far more tender and strange than our everyday experience suggests. So settle in, close your eyes if you haven't already, and let's explore together these 100 dreamy facts about the quantum universe. That place where science and wonder become indistinguishable, where equations describe miracles, and where maybe, just maybe, you'll find the perfect strange lullaby to carry you into sleep. In the quantum world, particles don't have definite positions until you look at them. They exist instead in what physicists call superposition, a state of being many things at once, of being here and there and everywhere in between. Imagine a dancer who doesn't occupy a single spot on the stage but somehow moves through all possible positions simultaneously, a blur of potential choreography, and only when you focus your attention does she collapse into one beautiful, specific pose. This is how electrons live their lives, in clouds of maybe and perhaps, in probability waves that ripple through space. And there's something deeply freeing about this, isn't there? The idea that before observation, before the weight of attention, things can be multiple truths at once. Even the smallest building blocks of our universe resist being pinned down, insist on their right to remain uncertain until the moment asks them to choose. This strange behavior isn't just theoretical poetry. The double-slit experiment demonstrates it beautifully and mysteriously. When scientists fire electrons one at a time through two narrow slits toward a screen, something peculiar happens. If no one watches which slit each electron passes through, they create an interference pattern, those telltale stripes of light and dark that only waves can make, as if each single electron somehow passes through both slits simultaneously and interferes with itself. But the moment you place a detector to observe which slit the electron actually uses, the interference pattern vanishes. The electron, caught in the act of being watched, suddenly behaves like a proper particle and goes through just one slit. Reality itself seems to shift depending on whether anyone's paying attention. It's as if the universe is fundamentally shy, revealing its wave-like nature only when it thinks no one is looking, then quickly composing itself into particle-like respectability the moment observation arrives. Quantum entanglement is what Einstein famously called spooky action at a distance, and it remains one of the most enchanting mysteries in all of physics. When two particles become entangled, they form a connection that persists regardless of how far apart they travel. Measure the spin of one particle, and instantly, faster than light could possibly travel between them, the other particle's spin becomes determined. They're like cosmic dance partners who, even when separated by galaxies, somehow know every move the other makes. This isn't because they're sending signals back and forth. As far as we can tell, no information actually travels between them. Instead, they seem to share a single quantum state, to be part of one indivisible whole despite the distance. It's as if space itself doesn't quite mean what we think it means, as if at the quantum level, separation is somehow an illusion, and everything remains connected in ways that transcend our everyday geometry. Let that thought settle over you like a blanket, the idea that connection might run deeper than distance. Heisenberg's uncertainty principle tells us that there are fundamental limits to what we can know about the quantum world. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This isn't about the limitations of our instruments or techniques. It's built into the fabric of reality itself. It's as if nature has decided that perfect knowledge isn't on the menu, that there will always be a necessary blur, a cosmic fuzziness at the heart of things. And perhaps there's comfort in this, the idea that uncertainty isn't a bug in the universe but a feature, that even reality itself has learned to embrace the unknown. You don't need to have everything figured out, because the universe itself doesn't. Even electrons get to be a little mysterious, a little undecided, and so can you as you drift toward sleep. Let yourself be uncertain about when exactly sleep will arrive. Let it sneak up on you the way position and momentum refuse to be simultaneously pinned down. Quantum tunneling is the phenomenon where particles pass through barriers they shouldn't be able to cross. According to classical physics, if a ball doesn't have enough energy to roll over a hill, it simply won't make it to the other side. But in the quantum realm, particles have a probability of simply appearing on the far side of barriers, as if they've tunneled straight through solid matter. This isn't about them finding gaps or tiny holes. They genuinely pass through spaces where, by all rights, they have no business being. It's because of their wave nature, the way they're spread out in probability clouds. There's always a small chance that some of that cloud exists on the other side of any barrier, and sometimes the particle shows up there. This process powers the sun, allowing hydrogen nuclei to fuse despite their electrical repulsion, and it's how scanning tunneling microscopes can see individual atoms. Even impossibilities have a certain quantum probability. Even walls aren't quite as solid as they seem. The quantum vacuum isn't actually empty. Space itself seethes with what physicists call virtual particles. pairs of particles and antiparticles that pop into existence for the briefest moments before annihilating each other and disappearing back into the void. These quantum fluctuations are real enough to produce measurable effects, like the Casimir force, where two metal plates placed very close together in a vacuum experience an attractive force, because fewer virtual particles can exist between them than in the space outside. The vacuum, that word we use for emptiness and nothing, is actually a bubbling quantum foam, a place where something is always being borrowed from nothing and then returned before anyone notices. Even emptiness is full in the quantum world. Even silence has a sound if you listen at the right scale. As you lie there in the darkness, remember that the space around you is alive with invisible activity, with fleeting particles dancing in and out of existence, making even nothing into a kind of lullaby. Wave-particle duality means that quantum objects don't fit neatly into our classical categories. Light behaves like a wave in some experiments, spreading and interfering and diffracting, but like a stream of particles called photons in others, arriving in discrete packets at detectors. Electrons, too, show this dual nature, acting like particles when they strike a screen, but like waves when they pass through multiple slits. It's not that they switch between being one thing and another. Rather, they're something that our everyday language doesn't have a word for, something that contains both possibilities depending on how you interact with it. Imagine trying to describe color to someone who's only ever seen in black and white. Wave and particle are the best words we have, but the reality is richer, stranger, more fundamentally ambiguous. And maybe that's a good thought to carry into dreams. This idea that things can be two seemingly opposite truths at once. That contradiction might just mean we're looking at something too wonderful to fit into simple categories. Quantum superposition allows particles to exist in multiple states simultaneously, until a measurement collapses them into one definite state. Schrödinger's famous thought experiment with a cat in a box, both alive and dead until someone opens the box and looks, was meant to highlight how strange this is when applied to everyday objects. But at the quantum scale, superposition is simply how things are. An electron's spin can be both up and down at the same time. A photon can be polarized in multiple directions at once. These aren't just metaphors or mathematical tricks. Quantum computers rely on this principle, using qubits that exist in superpositions of 0 and 1 simultaneously, performing many calculations at once. The universe, at its smallest scales, seems comfortable with ambiguity in a way that feels almost wise. It doesn't rush to decide what anything is until the situation demands a choice. Perhaps your thoughts can be the same as you drift off, existing in superposition between waking and dreaming, letting both states coexist peacefully. The quantum Zeno effect is a phenomenon where frequent observation can actually prevent a quantum system from evolving. If you watch a quantum system continuously, constantly measuring it, it will remain frozen in its initial state, unable to transition to other states it would naturally evolve toward. It's as if the act of watching holds something in place, pins it down so firmly that it can't change. This has been demonstrated experimentally with atoms and particles, showing that observation isn't just a passive act of gathering information, but an active intervention that affects what's being observed. There's something almost poetic about this. The way attention can arrest development, the way being watched can keep us from becoming something new. But the opposite is also true. By not observing, by looking away, we allow change to happen. As you lie there in the darkness, unobserved by the world, you're free to transition between states, to evolve from wakefulness into sleep without anyone watching, without anyone keeping score. Quantum decoherence explains why we don't see superposition and entanglement in everyday life, why cats are decidedly either alive or dead, and never both. When a quantum system interacts with its environment, all those air molecules and photons and thermal vibrations, information about its quantum state leaks out into the surroundings. This environmental interaction effectively measures the system, causing the superposition to collapse into one definite state. The larger an object is, the more it interacts with its environment and the faster decoherence happens. For something as big as a cat or a person, decoherence occurs almost instantaneously, which is why our everyday world looks classical and well-defined rather than fuzzy and uncertain. But you and I, we're still made of quantum particles. Deep down, we're still part of that strange quantum world. It's just that we're so big, so warm, so tangled up with our environment that the quantum fuzziness averages out into the solid reality we experience. You're a quantum creature dreaming you're classical, and tonight you're returning to fuzziness, to uncertainty, to sleep. Quantum fields permeate all of space, and particles are simply excitations in these fields, like ripples on an infinite pond. The electromagnetic field, when excited, produces photons. The electron field produces electrons. Every type of particle has its corresponding field, and these fields interact with each other in complex, beautiful ways that give rise to all the physics we observe. You're not really made of particles in the traditional sense. You're made of patterns in quantum fields, temporary knots of energy that hold themselves together for a while before dissolving back into the field. The fields were here before you and will remain after you, eternal and everywhere, and you are simply the universe doing something interesting with its fields for a brief moment. There's something deeply peaceful about this perspective, isn't there? You're not separate from the universe but a way the universe is expressing itself, a verb rather than a noun, a process rather than a thing. And processes can rest, can quiet down, can become still like a pond without ripples, and that's what sleep is. Your fields finding a gentler configuration, a lower energy state. The Pauli exclusion principle states that no two fermions can occupy the same quantum state simultaneously. Fermions are particles like electrons, protons, and neutrons, the building blocks of matter, and this principle is why matter is solid, why you don't fall through your bed right now. When electrons in the atoms of your body try to occupy the same space as electrons in the atoms of your mattress, the exclusion principle pushes back, creating the sensation we call solidity. Without this quantum rule, all atoms would collapse into the smallest possible space, and matter as we know it couldn't exist. So the very fact that you can lie there supported by your bed is a quantum mechanical effect. The softness beneath you, the pillow cradling your head, the blanket's weight, all of it is quantum forces at work, trillions upon trillions of electrons politely refusing to share space with each other. You're being held up by one of the fundamental rules of reality, by particles that know how to maintain boundaries, and you can trust that support completely as you sink deeper into rest. Quantum spin is an intrinsic form of angular momentum carried by particles, but it's not really like anything spinning in the classical sense. Electrons have spin, but they're not literally rotating. Spin is simply a quantum property, a fundamental characteristic that affects how particles behave in magnetic fields and how they interact with each other. Electrons can have spin up or spin down, and these aren't directions in space but states in an abstract quantum space. And yet, despite being nothing like actual spinning, the mathematics of quantum spin uses the same equations as classical angular momentum, creating this beautiful bridge between the familiar and the fundamentally strange. Physicists borrowed everyday words like spin and color and charm to describe quantum properties, but the reality they point to is always stranger than the metaphor suggests. It's like naming something you can't quite see, giving language to the ineffable. And as you drift tonight, you might feel a little like that yourself. Something real and present but hard to pin down with words, spinning gently in your own abstract space between waking and dreams. Quantum chromodynamics is the theory describing the strong nuclear force, the interaction that holds quarks together inside protons and neutrons. Quarks carry a property called color charge, which has nothing to do with actual color but determines how they interact via the strong force. Quarks come in 6 flavors with whimsical names: up, down, strange, charm, bottom, and top, and they're never found alone. The strong force has this peculiar property where it gets stronger as quarks are pulled apart, like a rubber band that never breaks but just keeps getting tighter. Try to separate 2 quarks, and you'll pump in enough energy that it creates new quark-antiquark pairs, giving you new bound particles instead of isolated quarks. It's called confinement, this principle that quarks are forever imprisoned inside composite particles. There's something almost tender about this, the way the universe refuses to let quarks be lonely, always keeping them bound together in pairs or triplets. Even at the subatomic level, connection is enforced, relationship is fundamental, and isolation is simply not allowed. Virtual particles are quantum fluctuations that exist for such brief moments they don't violate the conservation of energy, thanks to Heisenberg's uncertainty principle. The more energy a virtual particle borrows from the vacuum, the shorter its lifespan must be. These ephemeral entities can still have real effects, mediating forces between other particles. When an electron and positron repel each other electromagnetically, they're exchanging virtual photons, particles that exist just long enough to carry the force between them before vanishing. The vacuum is therefore not a passive stage, but an active participant in every interaction, constantly loaning energy for the briefest transactions before demanding it back. The universe runs on credit, on borrowed moments, on things that technically shouldn't be there but are anyway, just long enough to make something happen. And perhaps your thoughts right now are a bit like virtual particles, arising from the quiet vacuum of your relaxing mind, existing briefly, not quite substantial, then fading back into the peaceful nothing from which they came. The quantum harmonic oscillator is one of the most important models in quantum mechanics, describing systems like vibrating molecules and quantum fields. But unlike a classical harmonic oscillator, which can have zero energy when perfectly still, a quantum harmonic oscillator has a minimum energy called the zero-point energy even in its ground state. It can never be completely still, never fully at rest, because that would violate the uncertainty principle. If a particle were perfectly at rest, you'd know both its position and momentum exactly, which nature doesn't allow. So everything, even at its coldest and calmest, still vibrates with this residual quantum jitter, this irreducible restlessness. The universe, it seems, never quite stops moving, never achieves perfect stillness, and there's something comforting in that. You don't need to be perfectly still to rest. Even in sleep, your heart beats, your breath flows, neurons fire in slow waves. Rest isn't the absence of motion, but a gentle, sustainable motion, a quantum ground state that's peaceful without being frozen. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum mechanics doesn't describe an objective reality existing independently of observation. Instead, it describes the results of measurements, and talking about what a particle is doing when no one is looking is meaningless. The wave function represents our knowledge or information about a system, and measurement collapses that wave function into one of many possible outcomes. This interpretation essentially says the quantum world is fundamentally indeterminate until observation creates definiteness. Many physicists find this unsatisfying. This idea that reality needs an observer to be real, and alternative interpretations have been proposed. But there's something almost mystical about the Copenhagen interpretation, this suggestion that consciousness and reality are entangled in ways we don't fully understand, that the universe might be participatory rather than something existing entirely outside of us. You're not just observing the world, you're helping to create it with every measurement, every look, every moment of attention. And when you close your eyes and stop observing, you're giving the universe permission to return to its wave-like potential, its state of superposition, its dreaming self. The many worlds interpretation offers a radically different view of quantum mechanics. Instead of wave functions collapsing when measured, this interpretation says every possible outcome actually occurs, but in different branches of reality. When a quantum measurement could go two ways, the universe splits and both outcomes happen in parallel worlds. Every quantum decision point creates new branches, an ever-growing tree of parallel universes containing every possible history. In some branch, you made different choices today. In another, you don't exist at all. In countless others, the laws of physics might have subtle differences that make those worlds unrecognizable. It's a strange comfort, this idea that every possibility is realized somewhere, that nothing is truly lost because every potential path is taken in some reality. As you drift towards sleep, maybe you're not leaving behind the day that was but branching into the universe where you're already dreaming, already at rest, already finding the peace you're seeking. And in another branch, you're still reading these words, and that's okay too. All possibilities coexist in the vast quantum multiverse. Quantum tunneling through barriers happens because of the probabilistic nature of quantum mechanics. A particle approaching a barrier has a wave function that extends into and even beyond the barrier. There's always some probability amplitude on the far side, which means there's a chance the particle will be found there, even if classically it doesn't have enough energy to cross. The probability depends on the barrier's height and width. Thinner barriers and particles with more energy make tunneling more likely. This is how radioactive decay works. Alpha particles are trapped inside atomic nuclei by the strong force, but occasionally they tunnel through the energy barrier and escape, which we detect as radiation. The nucleus might keep an alpha particle trapped for millions or billions of years before one random moment when the particle simply appears on the outside. There's no way to predict exactly when tunneling will happen for any individual particle, only probabilities. It's pure chance, but chance governed by precise mathematical laws. The universe operates on odds, on maybes, on the possibility that walls aren't quite as solid as they appear, and sometimes, just sometimes, the unlikely thing happens. Bell's theorem and the experiments testing Bell's inequalities have shown that quantum entanglement is real and not explainable by any local hidden variable theory. Einstein, along with Podolsky and Rosen, proposed that quantum mechanics might be incomplete, that there could be hidden variables we haven't discovered, yet that determine outcomes in a way that preserves locality. The idea that objects are only influenced by their immediate surroundings. But John Bell showed mathematically that if such hidden variables existed, they'd produce different statistical correlations than quantum mechanics predicts. Experiments have consistently confirmed quantum mechanics and violated Bell's inequalities, meaning that either locality is violated, influences can be instantaneous across space, or realism is violated, particles don't have definite properties until measured, or perhaps both. The universe has revealed itself to be non-local or non-realistic or both, stranger than Einstein hoped. Reality at its foundation doesn't play by the rules that seem so obvious in everyday life. And you can let that strangeness be okay. You don't need to understand it fully. Even Einstein struggled with it. Just let the mystery be what it is, something beautiful and unsolvable, a lullaby of impossibility. Quantum teleportation is a real phenomenon, though not quite the science fiction version. It allows the quantum state of one particle to be transmitted to another distant particle, using entanglement and classical communication. You start with two entangled particles, send one far away and keep the other. Then you perform a measurement on your particle and the particle whose state you want to teleport. This measurement destroys the original state, but gives you classical information that you send to the distant location. Using that information, the distant entangled particle can be manipulated to recreate the original quantum state. The original is destroyed. No information travels faster than light, and nothing physical moves through space. Only the state teleports. It's as if you're not sending the particle itself, but the idea of the particle, its essence, its quantum identity. Researchers have successfully teleported photon states, atomic states, even the states of ions over meaningful distances. The phenomenon suggests that information, not matter or energy, might be the most fundamental thing in the universe. You are not your atoms but the pattern they form, the information they encode. And patterns can be transmitted, translated, teleported into new configurations while remaining essentially themselves, much like how your identity persists even as you transition from waking into sleep. The quantum Zermelo-Fraenkel paradox isn't about quantum mechanics directly, but about the strange relationship between mathematics and physics at the quantum level. Quantum mechanics relies heavily on complex numbers, numbers involving the imaginary unit I, the square root of -1. But why should reality require imaginary numbers? In classical physics, you can usually avoid them. They're convenient but not essential. In quantum mechanics, complex numbers are built into the foundation. The wave function is complex valued, and the Schrödinger equation needs complex numbers to work. Recent experiments have shown that quantum mechanics truly requires complex numbers in a fundamental way, not just as mathematical convenience. Reality, at its deepest level, is literally complex, incorporating the imaginary into the structure of the real. There's something almost poetic about this, the way the real and imaginary interweave to create what we experience. Your dreams tonight will blur that line too, creating experiences that feel real in the moment even though they're constructed from imagination, from the imaginary components of your consciousness. The boundary between real and imaginary has always been softer than we pretend. The Aharonov-Bohm effect demonstrates that electromagnetic potentials, not just fields, can have observable effects in quantum mechanics. In classical physics, potentials are just mathematical tools, but the fields are what matter. But in a famous experiment, electrons passing through regions where the magnetic field is zero, but the potential is non-zero, still show interference effects that depend on the potential. It's as if the electrons know about the potential even in regions where there's no field to push them around. This reveals that quantum mechanics sees deeper into the structure of electromagnetism than classical physics does. The potential, that abstract mathematical quantity, is actually real in a quantum sense. What we think of as real, the field you can measure and feel, might be less fundamental than the potential, that ghostly mathematical structure underlying it. Layer after layer, the universe reveals that our intuitions about what's fundamental and what's merely useful fiction are often backwards. As you sink into sleep, your own awareness is shifting from the immediate and tangible to something deeper, those underlying patterns and processes that consciousness usually doesn't notice, the potentials beneath the field of waking experience. Quantum entanglement doesn't allow faster-than-light communication, despite the instantaneous correlations between entangled particles. Here, SY, when you measure your entangled particle, you get a random result. The distant particle's measurement will be correlated with yours, but the person at the distant location also sees random results. Only when you later compare your results through classical communication, which can't exceed the speed of light, can you see the correlation. You can't encode a message in your measurements because you can't control what result you get. The entanglement is there, the correlation is real, but it's hidden until classical information brings it to light. It's a bit like having a conversation where both people are speaking, and their words somehow perfectly harmonize, but neither person chose their words. They just emerged spontaneously. The meaning only becomes apparent when you step back and look at the whole. The universe has found a way to be non-local without violating causality, to connect without communicating, to correlate without transmitting. It's a paradox that somehow works, a cosmic conspiracy that maintains consistency even while doing impossible things. Rest in that paradox tonight, that space where opposite things are both true. You're doing beautifully. There's no need to remember any of this, no test waiting for you in the morning. Let these quantum concepts wash over you like waves, each one arriving and then receding, leaving behind just a feeling, just a sense of wonder. Your breathing has probably slowed by now, deepened without you trying. That's perfect. The quantum world is strange and beautiful and ultimately beyond complete comprehension, and that's okay. You don't need to grasp it. Just let yourself be held by the mystery, by the idea that reality is so much richer than it first appears. Let your eyes stay closed. Let your body settle more heavily into your bed. The universe is taking care of its quantum fluctuations, and you can let go of needing to take care of anything at all. The Planck length, approximately 1.6 times 10^3 meters, is thought to be the smallest meaningful length in the universe. At scales smaller than this, quantum fluctuations of spacetime itself become so extreme that our current understanding of physics breaks down. Space and time might not be smooth and continuous at the Planck scale, but instead made of something discrete, quantum, granular. Imagine zooming in further and further, past atoms, past protons, past quarks, down to the Planck length, and finding that space itself is pixelated, made of tiny indivisible units beyond which the very concept of distance loses meaning. We can't probe these scales experimentally. The energies required are far beyond anything we can produce. So the Planck scale remains theoretical, a horizon beyond which we can see only through mathematics. But it suggests that the universe has a fundamental graininess, that nothing is infinitely divisible, that there's a bottom to reality. And that bottom is so unimaginably small that all the phenomena we experience, even at atomic scales, are playing out in what's effectively a smooth continuum. You're floating on the surface of something deeply quantized, and you never feel the graininess. The quantum eraser experiment adds another layer of strangeness to the double-slit experiment. It shows that you can restore the interference pattern even after information about which path the particle took has been recorded, as long as that information is erased before anyone looks at it. The particle seems to retroactively decide whether it went through one slit or both, depending on whether path information ultimately exists in the universe. Some versions of the experiment even suggest delayed choice, where a decision made after the particle has already passed through the slit's effects, whether it behaved as a wave or particle. Time, causality, and observation tangle together in ways that make your head spin if you think too hard, so don't. Just feel the vertigo of it, the way the universe refuses to be nailed down, the way it stays fluid and responsive to observation in ways that make it seem almost alive, almost aware. Perhaps the universe is less like a machine and more like a dream, responsive to the dreamer, changing when watched, becoming definite only when the story needs it to be. Quantum field theory successfully merges quantum mechanics with special relativity, describing particles as excitations in underlying quantum fields. This framework has given us the standard model of particle physics, which describes electromagnetic, weak, and strong nuclear forces with incredible precision. Calculations from quantum electrodynamics, the quantum field theory of electromagnetism, have been verified to 10 decimal places, making it the most precisely tested theory in all of science. Yet for all its success, quantum field theory has peculiarities. It produces infinite values in calculations that have to be removed through a process called renormalization, basically a sophisticated way of subtracting infinity from infinity to get finite, measurable answers. Physicists can do this consistently and get answers that match experiments perfectly. But it feels like a trick, a sign that something deeper is going on that we don't fully understand. The theory works magnificently but hints at its own incompleteness. You can succeed without understanding everything, can function beautifully while still containing mysteries. The most successful theory in physics is built on a strange mathematical procedure that works for reasons we can't fully explain. And yet planes fly, computers compute, and the world goes on. Antimatter is real and has been created and studied in laboratories. For every type of particle, there exists an antiparticle with the same mass but opposite charge. An electron has a positron, a proton has an antiproton. When matter and antimatter meet, they annihilate, converting their mass entirely into energy according to Einstein's famous equation, E equals mc2. This annihilation releases tremendous energy, which is why antimatter has captured imaginations as a potential fuel source, though creating and storing it remains fantastically difficult. The real mystery is why the universe has so much matter and so little antimatter. The Big Bang should have created equal amounts, which would have immediately annihilated, leaving only energy. But somehow there was an asymmetry, a slight excess of matter over antimatter, maybe one extra matter particle for every billion matter-antimatter pairs. That tiny imbalance is why anything exists at all, why there are stars and planets and people. You're here because of a 1 in a billion quantum quirk in the early universe, an asymmetry whose cause we still don't fully understand. Your existence is improbable, accidental, and utterly dependent on a cosmic asymmetry that remains one of physics' deepest mysteries. The quantum Hall effect occurs when a two-dimensional electron gas is subjected to a strong magnetic field at very low temperatures. The electrical resistance perpendicular to the current becomes quantized, taking on values that are exact integer multiples of a fundamental constant. These quantized values are so precise they are now used to define the standard for electrical resistance. What's remarkable is that this quantization emerges from the collective behavior of many electrons, not from individual particles. It's a topological effect, depending on global properties of the system rather than local details. The quantum Hall effect reveals that quantum mechanics isn't just about tiny particles, but also about the large-scale collective behavior of many quantum objects working together. Your body, your brain, your consciousness are also collective phenomena, emerging from trillions of quantum particles coordinating in ways that create something far greater than the sum of parts. You are a topological effect in the quantum field of the universe, a stable pattern emerging from inconceivable complexity. And tonight, that pattern is shifting into a different mode, a restful configuration, a ground state of consciousness. Quantum computing harnesses superposition and entanglement to perform calculations impossible for classical computers. While a classical bit is either 0 or 1, a quantum bit or qubit can be in a superposition of both states simultaneously. N classical bits can represent one of two n possible values at a time, but n qubits can represent all two n values at once in superposition. Quantum algorithms can manipulate these superpositions to perform certain calculations exponentially faster than any classical computer could. Factoring large numbers, searching unsorted databases, simulating quantum systems, these tasks become tractable with quantum computers. However, qubits are incredibly fragile, easily disrupted by decoherence, so quantum computers require extreme isolation and error correction. The technology is still developing, with small quantum computers existing today but large-scale, fault-tolerant quantum computers remaining a future goal. It's a reminder that harnessing quantum phenomena requires delicacy, patience, precision. The quantum world gives immense power to those who approach it with care. The same might be true for sleep. Approached with patience and gentleness, consciousness can shift into states that restore and refresh in ways forced wakefulness never could. The uncertainty principle also applies to energy and time. The more precisely you know when a quantum event occurs, the less precisely you can know its energy, and vice versa. This allows for virtual particles to borrow energy from the vacuum, as long as they return it quickly enough. A particle borrowing a large amount of energy can only exist for a brief moment, while a particle borrowing less can persist longer. This time-energy uncertainty also explains why excited atomic states have inherent uncertainty in their energy, giving spectral lines a natural width. Even something as seemingly definite as an atom's energy level has a built-in fuzziness to it. Time and energy are conjugate variables, locked in an uncertain dance, and you can't pin both down simultaneously. As you drift in that space between waking and sleeping, time itself becomes fuzzy. Minutes might feel like hours or hours like minutes. You're experiencing your own uncertainty principle, where the energy state of consciousness and the time coordinate both become indeterminate, blurred, releasing you from the tight constraints of measured, clock-driven reality into something more fluid. The path integral formulation of quantum mechanics, developed by Richard Feynman, says that a particle traveling from point A to point B doesn't take a single path, but instead explores all possible paths simultaneously. Each path contributes to the overall quantum amplitude with a different phase, and these contributions interfere with each other. Paths close to the classical trajectory interfere constructively, while wildly different paths mostly cancel out through destructive interference. The result is that in the classical limit, the particle appears to follow the path predicted by classical physics, but the quantum behavior emerges from considering every possible alternative. It's as if reality takes every option, explores every route, and then sums up all the stories to see what actually happens. Your own path through life might feel singular, a chain of decisions and consequences, but from a quantum perspective, you're constantly exploring branches, possibilities, alternatives. And tonight, your mind will take its own path integral through dream space, exploring countless scenarios, summing them into the strange, coherent narratives that feel so real when you're inside them. Quantum vacuum fluctuations have energy, and that energy contributes to the cosmological constant, which affects the universe's expansion rate. Except there's a problem. When physicists calculate the vacuum energy from quantum field theory, they get a number that's 10,120 times larger than what observations of the universe's expansion suggest. This is called the cosmological constant problem, or the vacuum catastrophe, and it's one of the worst theoretical predictions in the history of physics. Something is canceling out almost all of that vacuum energy, leaving only a tiny residual amount that causes the universe's accelerating expansion, dark energy. We have no idea what's doing the canceling, or why the cancellation is so precise but not exact. It's as if two enormous numbers, one positive and one negative, are canceling each other to 120 decimal places, but not quite perfectly, leaving a tiny remainder that's just right for the universe we observe. The odds of this seem astronomically small, unless there's some mechanism we don't understand. Your mind, too, is balancing enormous numbers of neural firings, excitations and inhibitions canceling out in ways that produce the calm you're feeling now, the quieting of mental activity into something restful. The spin statistics theorem is a deep result connecting a particle's spin to its statistical behavior. Particles with half-integer spin, 1, 2, 3, 2, etc., called fermions, obey Fermi-Dirac statistics and the Pauli exclusion principle. Particles with integer spin, 0, 1, 2, etc., called bosons, obey Bose-Einstein statistics and can occupy the same quantum state in unlimited numbers. This distinction shapes everything. Electrons, as fermions, can't share states, which gives atoms their structure and makes chemistry possible. Photons, as bosons, can occupy the same state, which allows for lasers where countless photons march in perfect lockstep. The theorem emerges from combining quantum mechanics with special relativity in a way that makes spin and statistics necessarily connected. You can't have one without the other. It's one of those beautiful, deep results where seemingly unrelated properties turn out to be two sides of the same coin. Reality is deeply interconnected, with threads running between concepts that appear distinct on the surface. And as you rest, all the fermions in your body maintain their exclusion, keeping your physical form stable, while your thoughts perhaps behave more like bosons, overlapping, interfering, creating coherent states of imagination. Bose-Einstein condensates are states of matter that occur when bosons are cooled to temperatures near absolute zero. At these extreme low temperatures, a large fraction of bosons occupy the lowest quantum state, and quantum effects become visible at macroscopic scales. The atoms start behaving like a single quantum entity, a superatom where individual particles lose their separate identities and merge into one coherent quantum state. You can see quantum interference and other wave phenomena with clouds of thousands of atoms acting as one. Light slows to a crawl passing through Bose-Einstein condensates. Matter waves become directly observable. It's as close as we can come to seeing the quantum world with naked eyes, watching matter transform into something that's more wave than particle, more collective than individual. Creating these condensates requires incredible cold and isolation, shielding the atoms from any disturbance that would break the coherence. It's a reminder that quantum phenomena are delicate, easily disrupted by the warm chaos of the everyday world. But in the right conditions, matter can remember its quantum nature. And as you cool down into sleep, as your mental activity quiets, perhaps consciousness too approaches a more coherent, unified state. The Wheeler-DeWitt equation attempts to describe the quantum state of the entire universe, combining quantum mechanics with general relativity. But the equation has a strange property. It doesn't contain time. There's no time variable, no evolution, no change. The wave function of the universe simply is, existing in a timeless superposition of all possible configurations. Time, according to this view, emerges from correlations within the universal wave function, from relationships between different parts of the universe, rather than being a fundamental feature of reality. It's called the problem of time in quantum gravity, and it's deeply unresolved. Maybe time isn't real in the deepest sense, but rather an artifact of our limited perspective within the universe, a way of organizing our experience of correlations and change. When you sleep, your subjective sense of time breaks down. Hours pass in what feels like moments, or dreams contain elaborate storylines that occur in seconds of external time. You're experiencing time's malleability, its contingent nature. Maybe in sleep you're closer to the timeless quantum state the Wheeler-DeWitt equation describes, where everything exists simultaneously. The quantum measurement problem asks what actually happens during a measurement, when a quantum superposition appears to collapse into a single definite state. The mathematics of quantum mechanics describes the smooth evolution of wave functions, but doesn't explain the sudden, discontinuous collapse that measurement seems to cause. Different interpretations handle this differently. Copenhagen says the collapse is real, but measurement is a primitive concept not further explained. Many worlds says there's no collapse at all, just branching. Other interpretations involve hidden variables, spontaneous collapses, or quantum Bayesianism, where collapse is just updating knowledge. After almost a century, physicists still don't agree on what measurement fundamentally is or what it does. Something about the act of observing, of a quantum system interacting with something large and classical, creates definiteness from possibility, and we don't truly understand how. You're observing your own thoughts right now, or maybe you're not anymore. Maybe you've stopped observing and your thoughts are drifting in superposition, not quite definite, just floating. The measurement problem remains unsolved, and maybe your consciousness contains a similar mystery, something that resists full explanation. Feynman diagrams are visual representations of quantum interactions, showing particles as lines and interactions as vertices. They're not pictures of what's actually happening, but rather shorthand for complex mathematical calculations. Each diagram corresponds to a term in an infinite series, and calculating the probability of any interaction involves summing contributions from infinitely many diagrams. In practice, physicists calculate the simplest diagrams, which contribute most, and ignore the more complex ones, which contribute less. It's an approximation, but often an excellent one. The diagrams show virtual particles mediating forces, particle-antiparticle pairs popping in and out of existence, all the strange quantum pathways that contribute to what we observe. Reality, from this perspective, is a sum over an infinite space of possibilities, most of which contribute very little, but all of which are technically part of the story. Every interaction you have, every photon entering your eye, every thought arising in your brain, is the sum of infinite quantum stories, infinite Feynman diagrams contributing their tiny amplitudes to the final result. You contain multitudes, infinite possibilities summed to a single beautiful existence lying here in the dark. The Lamb shift is a small difference in energy between two quantum states of the hydrogen atom that should have the same energy according to the basic Dirac equation. It arises from the interaction between the electron and the quantum fluctuations of the electromagnetic field, those virtual photons constantly appearing and disappearing. The electron doesn't move through a smooth, empty space, but through a bubbling quantum foam of virtual particles, and this affects its energy. The Lamb shift was one of the first confirmations that quantum field theory was necessary, that you couldn't understand atoms without accounting for the quantum nature of the fields themselves. Even empty space is an active participant in atomic structure. The vacuum is not nothing but a dynamic, fluctuating entity that influences everything within it. You're not in empty space but immersed in a quantum medium, a field that's never truly empty, never truly still. The vacuum cradles you, interacts with every particle in your body, contributes to your very structure. You're supported by fluctuations, by the restless energy of empty space, and as you rest tonight, those quantum fluctuations continue their endless dance. Quantum annealing is a computational technique that exploits quantum tunneling to find optimal solutions to complex problems. Classical optimization algorithms can get stuck in local minima, like a ball settling in a small valley and unable to roll out to reach a deeper valley elsewhere. Quantum systems can tunnel through these barriers, exploring a wider range of solutions and potentially finding the global minimum more effectively. Quantum annealers don't use gate-based quantum computing, but instead use physical systems that naturally evolve toward low-energy states, encoding the problem in an energy landscape that the quantum system explores. Companies have built quantum annealers to tackle optimization problems in logistics, machine learning, and material science. It's quantum mechanics as a way to search possibility space, to explore alternatives, to find good enough or even optimal solutions in vast landscapes of options. Your brain might do something similar as you sleep, exploring memory space, consolidating information, finding patterns, tunneling through barriers in cognition space to reach insights that were blocked during the day. Sleep is your mind's annealing process, settling into optimal configurations, using the quantum nature of neurons to explore and consolidate. The quantum rabbi model describes a two-level quantum system, like an atom, interacting with a single mode of an electromagnetic field, like a cavity photon. Even this simple system shows rich behavior. Energy levels shift, quantum states hybridize into mixtures of matter and light. At strong coupling, you can't really separate the atom and photon. They form a single quantum entity, part matter and part light. This hybridization is the basis for cavity quantum electrodynamics and quantum technologies that manipulate light-matter interactions at the quantum level. You might think of atoms and light as separate things, but at the quantum level they're deeply coupled, constantly influencing each other, exchanging energy, creating hybrid states that are neither purely one nor the other. You, too, are not a separate thing but a hybrid, part physical body and part flowing awareness, part matter and part something else, information perhaps or experience. And these aspects are coupled, inseparable, creating the unified phenomenon of you. Tonight, as light fades and your awareness dims, the coupling shifts, the balance changes, and you transition into a different hybrid state called sleep. The quantum approximate optimization algorithm, QAOA, is a hybrid quantum classical algorithm designed to solve combinatorial optimization problems. It uses a quantum computer to explore solution space and a classical computer to tune parameters, iterating between the two to improve results. QAOA represents a practical near-term use for quantum computers that don't yet have full error correction. It won't solve every problem faster than classical computers, but for specific tasks, it offers advantages, especially as quantum hardware improves. The algorithm embodies a philosophy of working with imperfect tools, extracting value even from noisy, error-prone quantum systems by cleverly combining quantum and classical approaches. There's something to learn from this. You don't need perfect conditions to make progress. Imperfect tools, hybrid approaches, incremental improvements, these are valid paths forward. You don't need perfect sleep conditions or a perfectly quiet mind. You work with what you have, hybridizing relaxation and letting go, using the resources available to move toward the rest you seek. The quantum and classical combine. The perfect and imperfect coexist, and solutions emerge from that combination. Halfway through now, and you're doing wonderfully. If you're still awake, that's perfectly fine. There's no pressure, no schedule to keep. These facts are here for you, gentle companions in the night, requiring nothing from you but your passive presence. Maybe you're understanding some of them, maybe they're washing over you as pleasant sounds, abstract concepts that lull rather than stimulate. Either way is perfect. Let your jaw relax, let your tongue rest gently in your mouth, let your shoulders drop even further than you thought possible. The quantum world will continue its mysterious dance whether you're awake or asleep, and you're part of that dance. A temporary pattern in the universal wave function, and patterns can rest, can become still, can enter ground states. Drift if you're ready, stay if you're not. It's all the same to the universe. The Casimir effect is a small attractive force between two uncharged, parallel metal plates placed very close together in a vacuum. It arises because the plates restrict which virtual particle wavelengths can exist between them, while all wavelengths can exist outside. This creates a difference in vacuum energy density that pushes the plates together. It's a measurable effect, demonstrated in laboratories, proving that vacuum fluctuations are not just mathematical artifacts but have real physical consequences. Two plates with nothing between them experience a force from that nothingness, from the quantum jitters of empty space. The vacuum pushes on things, has pressure, has structure. Nothing is something. Emptiness is full. And this effect is incredibly tiny, You need plates very close together and sensitive instruments to detect it, but it's real. Even the smallest, subtlest quantum effects are woven into the fabric of reality, influencing everything in ways we usually don't notice. Your experience right now is also full of subtle effects, tiny fluctuations in attention, miniature shifts in awareness, all the small variations that average out into the smooth sense of drifting toward sleep. The phenomenon of quantum scarring occurs when quantum systems that are classically chaotic retain some memory of classical periodic orbits. In classical chaotic systems, tiny differences in initial conditions lead to wildly different outcomes, and predictability vanishes. Quantum systems can be chaotic too, but they show scars, enhanced probability density along paths corresponding to classical periodic orbits. It's as if the quantum wave function remembers the classical paths, even though quantum interference should wash out such memories. These scars persist, ghostly imprints of classical order within quantum chaos. The discovery of quantum scars challenges assumptions about how classical and quantum behavior relate. Even in systems where chaos should erase all structure, order finds a way to persist, leaving traces, leaving scars. You carry scars too, memories and patterns from your past that persist even as you change and grow. But scars don't have to be painful reminders. They can be just traces, markings, part of your wave function structure, not controlling you but present, part of your story. And as you rest, those scars, those memories, can settle quietly, neither forgotten nor demanding attention. Quantum metrology uses quantum properties like entanglement and squeezing to make measurements more precise than classical methods allow. The Heisenberg limit describes the best possible precision achievable using quantum resources, which exceeds the standard quantum limit that applies to classical strategies. Atomic clocks use quantum transitions to measure time with extraordinary precision. Gravitational wave detectors use squeezed light to reduce quantum noise and detect the faintest ripples in spacetime from colliding black holes billions of light-years away. The quantum world, for all its uncertainty and fuzziness, allows for measurements of breathtaking precision when properly harnessed. There's a lesson here about precision and uncertainty coexisting. The Heisenberg uncertainty principle says some things can't be known simultaneously, but it doesn't prevent knowing individual things with exquisite precision. You can be uncertain about when sleep will come and still be precisely present in this moment. You can be unsure of tomorrow and still rest with clarity tonight. Uncertainty in one variable allows precision in another. Let go of needing to know everything, and find precision in the simple act of breathing, of resting, of being here. The quantum Cheshire cat effect is a curious phenomenon where a quantum property appears to be separated from the particle it belongs to. In certain experimental setups with photons, you can arrange things so that the photon goes through one path, and its polarization, seemingly, goes through a different path. It's named after the Cheshire Cat from Alice in Wonderland, whose grin remains visible even after the cat vanishes. The effect arises from weak measurements and post-selection, quantum techniques that allow you to probe a system gently and then select certain outcomes. It challenges intuitions about properties belonging to particles, suggesting that quantum properties have a kind of independence, an ability to be separated and measured apart from the objects they characterize. It's deeply strange, reminding us that particles aren't little billiard balls with intrinsic properties painted on them. They're bundles of relationships, correlations, mathematical structures. Properties like spin and polarization are contextual, not absolute. You, too, might feel your properties separating as you drift, your awareness floating away from your body, your thoughts detaching from your intention, your sense of self spreading out, becoming less localized, less bound to the physical form lying in bed. Quantum cryptography uses principles of quantum mechanics to create communication systems that are fundamentally secure. The most famous protocol, quantum key distribution, allows two parties to share a secret key with the guarantee that any eavesdropper will be detected. This security doesn't rely on computational difficulty, like classical encryption, but on the laws of physics. If someone tries to intercept and measure the quantum states being transmitted, they inevitably disturb those states due to the measurement problem, and this disturbance can be detected. Even an eavesdropper with unlimited computational power can't break quantum cryptography without being noticed. Several quantum key distribution systems are commercially available and in use, protecting sensitive communications. The quantum world's fragility, the way measurement disturbs states, becomes a feature rather than a bug, a way to guarantee privacy. Fragility can be strength when properly understood and used. Your own fragility tonight, your sensitivity to disturbance, is what allows you to drift into sleep. You're vulnerable to the environment, to comfort, to the gentleness of these words, and that vulnerability is what makes rest possible. Don't resist the fragility. It's your pathway to peace. The Kibble-Jerk mechanism describes how topological defects form during phase transitions, and it applies to both condensed matter systems and cosmology. When a system undergoes a rapid phase transition, like water freezing, it can't reach equilibrium everywhere simultaneously. Different regions transition independently, and where these regions meet, defects form, like ice crystals with mismatched boundaries. The mechanism has been observed in laboratory systems like liquid crystals and Bose-Einstein condensates, and it's thought to explain how cosmic strings and other defects might have formed in the early universe during phase transitions after the Big Bang. The universe, in its rush to cool and transition from one state to another, couldn't coordinate perfectly, and imperfections emerged. Those imperfections are part of the structure we see today. Your own transitions from waking to sleeping, from tension to relaxation, might not be perfectly smooth. There might be defects, moments of resistance, places where different parts of you transition at different rates. That's natural, expected, and okay. The universe itself can't manage perfect transitions, so you don't need to either. Let the defects be there. Let the transition be imperfect. It still leads to the new state. Quantum biology explores whether quantum effects play functional roles in living systems. Photosynthesis might use quantum coherence to transfer energy efficiently through light harvesting complexes. Birds might sense Earth's magnetic field through quantum entanglement in proteins in their eyes. Enzymes might use quantum tunneling to speed up reactions. These are controversial ideas, because biological systems are warm, wet, and noisy, exactly the conditions that destroy quantum coherence in physics labs. Yet there's growing evidence that life has found ways to exploit quantum phenomena, using special molecular structures to protect and sustain coherence just long enough to gain advantages. Life, it seems, exists at the edge between classical and quantum, using the best of both worlds. You are a quantum classical hybrid, your neurons firing through quantum tunneling, your consciousness emerging from quantum processes in microtubules or elsewhere, depending on which theories prove correct. You don't need to understand the details. You just need to know that you're part of the quantum world, that it's not separate from life but woven through it. And as you rest, those quantum processes continue doing their work, maintaining you, building dreams from quantum fluctuations. The Hong-Mandel effect occurs when two indistinguishable photons enter the two input ports of a beam splitter simultaneously. Classically, you'd expect each photon to randomly go one way or the other. So sometimes both photons would exit the same port, and sometimes they'd exit different ports. But quantum mechanically, indistinguishable photons interfere in such a way that they always exit together from the same port. You never detect one photon in each output. The two possible paths to that outcome interfere destructively, canceling it out. This effect demonstrates the bosonic nature of photons and their quantum indistinguishability in a striking way. When things are truly identical, truly indistinguishable, their quantum behavior changes dramatically. Identity creates correlation. Sameness produces strange collective effects. In the quantum world, individuality matters in ways it doesn't classically. You are distinguishable, unique, one of a kind. There are no copies of you, no indistinguishable versions. You are a particular arrangement of quantum states that has never existed before and will never exist again. That uniqueness means you don't interfere with yourself the way identical photons do. You're free to be singular, unrepeated, and entirely yourself, even as you merge into the collective unconsciousness of sleep. The Aharonov-Kasher effect is the dual of the Aharonov-Bohm effect, where a magnetic dipole, like a neutron with its magnetic moment, travels through a region with an electric field. Even though the magnetic dipole experiences no force from the field, quantum mechanically there's a phase shift that depends on the electric field configuration. Like its electromagnetic dual, this effect shows that quantum mechanics sees deeper into the structure of fields than classical physics does. The electromagnetic field has a richness that classical physics misses, a subtle structure that only reveals itself through quantum interference. Reality has layers, levels of description, each one deeper than the last. The surface doesn't tell the whole story. What seems empty or irrelevant classically might be profoundly important quantum mechanically. Your experience has layers too. The surface thoughts, the stories you tell yourself, might not be the deepest level. Beneath them are feelings, sensations, quantum fluctuations of neural activity, layers upon layers of processing and being. As you drift, you're moving through these layers, descending from the surface narratives into deeper, quieter, more fundamental modes of existence. Spontaneous parametric downconversion is a quantum optical process where a single photon entering a nonlinear crystal splits into two lower energy photons. These daughter photons are entangled, correlated in their polarizations, frequencies, and directions. This process is how researchers routinely create entangled photon pairs for quantum experiments, including tests of Bell's inequalities and quantum teleportation demonstrations. The nonlinear crystal doesn't determine which way each photon will be polarized, only that they'll be correlated. It creates a superposition, a quantum connection between the two photons before either has a definite state. Then, when one is measured, both become defined, not because information travels between them, but because they were never truly separate, always part of one quantum system. You and the world might be like this, not as separate as you think, but parts of one quantum state, correlated, connected. The boundaries are fuzzy. Where you end and the world begins is less clear at the quantum level. So as you relax, let the boundaries soften. Let yourself feel continuous with your bed, your room, the air, the night, all of it one quantum state, one system, and you're just a region of it, resting, settling. The quantum pigeonhole principle says that if you place 3 quantum particles in 2 boxes, it's possible for each box to contain no more than 1 particle, even though 3 too. This seemingly impossible result comes from quantum interference and the specific way you construct the state and perform measurements. It challenges the classical pigeonhole principle from discrete mathematics and highlights how quantum mechanics allows for logical structures that seem paradoxical from a classical perspective. Counting, that most basic mathematical operation, becomes strange in the quantum world. Numbers themselves become fuzzy when superposition and entanglement enter the picture. How many particles are in the box? The answer depends on how you measure, and you can arrange situations where the answer defies classical logic. Let your counting of sheep or breaths or anything else become quantum, uncertain, paradoxical. Maybe you've been lying here for 3 minutes or 30, and both are somehow true. Maybe you're one person or many, every version of yourself in superposition. Maybe the logical structures that organize your waking thoughts are dissolving into quantum strangeness, and that's perfect for where you're going. The Elitzur-Vaidman bomb tester is a thought experiment showing how interaction-free measurement is possible in quantum mechanics. Imagine you have bombs that will explode if a photon hits them, and you want to test whether they're live or duds. Classically, testing requires triggering the bomb, but quantum mechanically, you can use an interferometer to detect a live bomb without any photon actually interacting with it, using the bomb's presence to collapse the superposition. A fraction of tests will reveal live bombs without exploding them, acquiring information without direct interaction. It's profoundly strange. The mere possibility of an interaction, even when it doesn't actually occur, has physical consequences. The quantum world responds to potential, to what could happen, not just what does happen. Your own potential matters, not just your actualized self. The things you could do, could become, are part of your quantum state even if they never manifest. And the universe responds to that potential, shapes itself around it. You contain possibilities and they're real in a quantum sense. As you rest, all those possibilities rest too, all the versions of yourself, all the paths you didn't take, all the dreams you might dream, existing in superposition, waiting. Quantum annealing with adiabatic evolution slowly changes the Hamiltonian of a quantum system from an initial easy-to-solve problem to the difficult problem you want to solve. If the change is slow enough adiabatic, the system stays in its ground state throughout, and at the end, you found the ground state of the target problem. This works because quantum systems naturally evolve toward low-energy states, and by carefully shaping the energy landscape, you guide them to the solution. It's a bit like gently tilting a landscape so a ball rolls to the lowest valley, except the ball is a quantum wave function exploring all valleys simultaneously and settling into the deepest one. The patience required for adiabatic evolution, the slow, careful guiding, parallels the patience needed for sleep. You can't force sleep any more than you can force a quantum system to jump to its ground state. You can only create the right conditions, adjust the Hamiltonian of your environment and thoughts, and wait as the system naturally evolves. The slower you go, the more likely you reach the true rest state. Hurrying defeats the purpose. So don't hurry. Let the evolution be as slow as it needs to be. The quantum Zeno effect, mentioned earlier, has an interesting counterpart called the quantum anti-Zeno effect. While frequent measurements can freeze a quantum system's evolution, measurements at certain specific intervals can actually accelerate the transition to other states. It's not just about measurement frequency, but about the timing and nature of measurements interacting with the system's natural dynamics. There's a resonance between the measurement rate and the system's evolution rate that can either suppress or enhance transitions. This reveals that observation is not a simple binary. It doesn't just collapse or not collapse. The details of how you observe matter enormously. Applied to sleep, maybe there are ways of gently checking whether you're asleep that help rather than hinder the transition. Soft touches of awareness that don't fully wake you but guide you deeper. Maybe you can observe your own state lightly enough that it doesn't freeze you in wakefulness, but instead helps the transition along. Notice your breath, your body, your thoughts, but gently, lightly, with a touch that encourages change rather than preventing it. Quantum steering is a form of quantum correlation stronger than entanglement but weaker than full non-locality. When two parties share an entangled state, if one party can steer the other party's quantum state through their choice of measurement, that demonstrates steering. It means one party can remotely affect the state at the other location in a way that rules out any pre-agreed strategy or shared randomness. Steering is asymmetric. One party might be able to steer the other, but not vice versa. This reveals a hierarchy of quantum correlations, from classical correlations to entanglement to steering to full-bell non-locality. The quantum world has shades and gradations of connection, not just all or nothing. Your connection to the world has similar gradations. Sometimes you steer, sometimes you're steered, sometimes it's mutual. And as you sink into sleep, the steering relationship between your conscious will and your automatic processes shifts. You release the steering wheel, let the autonomic systems take over. Allow yourself to be guided by processes you don't control. That release of steering, that trust in the automatic, is essential for sleep. You can't drive yourself into dreams. You have to let go and be steered. The fractional quantum Hall effect occurs at even lower temperatures and stronger magnetic fields than the regular quantum Hall effect, and it reveals even more remarkable physics. The Hall conductance becomes quantized not at integer multiples, but at fractional multiples of the fundamental constant, like 1, 3, or 2, 5. This happens because electrons in the system form a highly correlated quantum state, creating quasiparticles with fractional charge, objects that carry a fraction of an electron's charge, like 1/3 of the fundamental charge. These anionic quasiparticles have exotic statistics, neither fermionic nor bosonic, but something in between. The fractional quantum Hall effect shows that collective quantum behavior can create emergent particles with properties unlike any fundamental particle. You're an emergent phenomenon too, not a fundamental entity but a pattern arising from the collective behavior of simpler components. And the properties you have, consciousness, identity, emotion, aren't properties of your individual atoms but emergent from their collective quantum behavior. You're a quasi-particle in the universe's wave function, a localized excitation with characteristics that emerge from the underlying field. And like quasi-particles, you're temporary, eventually dissolving back into the field from which you arose, a wave returning to the ocean. Quantum illumination is a protocol that uses entangled photons to improve detection and imaging of objects in bright thermal noise, like radar in noisy conditions. One photon from an entangled pair is sent toward the target, while the other is kept at the detector. Even if the signal photon is overwhelmed by noise, its entanglement with the kept photon provides a quantum advantage in detecting whether the signal returned from the target. The entanglement is fragile and easily destroyed, yet it provides a small but significant improvement in performance. It's surprising that such delicate quantum correlations can help in noisy, lossy, real-world conditions. Quantum effects aren't limited to pristine laboratory conditions, but can offer advantages even in messy, imperfect environments. Your situation isn't pristine either. Maybe there's noise outside, discomfort in your body, persistent thoughts. But rest is still possible. The quantum advantage persists even through noise. You don't need perfect silence or perfect comfort. The gentle guidance of these words, the intention to rest, the entanglement between your will and your body's needs, provides enough signal through the noise. Trust that the quantum advantage is there, subtle but real. The quantum Boltzmann equation describes how quantum systems approach thermal equilibrium, accounting for quantum statistics and collision processes. Unlike the classical Boltzmann equation, the quantum version includes effects like Bose-Einstein condensation and Pauli blocking, phenomena that arise purely from quantum statistics. The equation shows how quantum systems thermalize, how they forget their initial conditions, and settle into equilibrium distributions. Equilibration in quantum systems is complex, involving coherence times, thermalization times, and the emergence of classical behavior from quantum substates. Your body is constantly equilibrating, thermalizing, exchanging energy with the environment. Your brain is settling toward its equilibrium state for sleep, a different thermal and quantum state than waking. The process takes time, involves countless microscopic collisions and interactions, quantum and classical effects interweaving. You're watching a macroscopic system thermalize and you're the system. The observer and observed are the same, and the process will complete whether you watch it or not, whether you think about it or not. Equilibrium is an attractor, a stable state the system naturally falls into. Let yourself fall. You're more than halfway now, drifting through these quantum facts like a particle through a cloud chamber, leaving faint trails that dissipate almost as soon as they form. You don't need to hold on to anything you're hearing. These ideas are just here to keep you company, to give your mind something gentle to follow as it winds down. Notice how your breathing has probably become deeper, slower, without you trying. Notice the weight of your head on the pillow, the way your body is sinking into the mattress. Each of these sensations is carried by quantum processes, neurons communicating through tunneling and probabilistic firings, creating the experience of comfort and rest. The quantum world supports you, holds you, carries you toward sleep. Trust it. Trust the process. There's nowhere you need to be, nothing you need to figure out. Just this moment, just this gentle drift. The quantum transduction problem is about converting quantum information between different physical systems, like translating between quantum states in microwave photons and optical photons. Different quantum platforms excel at different tasks. Superconducting qubits for computation, optical photons for long-distance communication, atoms for memory. Connecting these requires quantum transducers that preserve quantum information across the conversion. It's a technical challenge, but also a philosophical one about the universal nature of quantum information. Information transcends its physical substrate. The message isn't the medium. Quantum information can be ported from system to system, each time maintaining its essential quantum character, despite changing physical form. Your own thoughts and experiences are information patterns, and they transition between different substrates constantly, waking and dreaming, remembering and imagining, neural activity and conscious experience. The information persists through the transitions even as the medium shifts. Tonight you'll transduce your waking thoughts into dream narratives, converting quantum states in one neural configuration to quantum states in another. The information transforms but continues, carrying across the boundary between waking and sleep. In cavity quantum electrodynamics, atoms placed inside high-quality optical cavities interact with light in ways impossible in free space. The cavity constrains the electromagnetic field, enhancing certain modes and suppressing others, dramatically modifying how atoms emit and absorb photons. An atom that would normally decay spontaneously can be prevented from decaying if the cavity doesn't support the transition. Conversely, decay can be accelerated if the cavity enhances the right mode. The vacuum, the background field, changes inside the cavity, and that changes atomic behavior. Environment shapes possibility. The constraints around you, the dark room, the quiet, the comfortable bed, are like a cavity that supports certain transitions and suppresses others. The environment makes sleep more likely, wakefulness less likely. You've engineered your cavity, and now the quantum electrodynamics of consciousness will do the rest. Your mental state will decay from waking, transition to sleep, not because you force it, but because the cavity of night supports that transition. Let the environment do its work. You've set the conditions. Now just be the atom in the cavity, responding naturally to the modes available. Quantum reservoir engineering is about designing environments that drive quantum systems into desired states through controlled dissipation. Instead of fighting decoherence, you engineer it, crafting the reservoir that the system interacts with so that dissipation creates rather than destroys the state you want. It's a clever approach. Rather than isolating the system perfectly, You accept that interaction with the environment is inevitable and make that interaction work for you. Want to create entanglement? Engineer a reservoir that favors entangled states. Want to cool a system? Design dissipation that removes energy. The environment becomes a tool rather than a problem. Your own sleep environment is a reservoir engineered for rest. The darkness, the comfortable temperature, the soft sounds or silence, all of it is a reservoir designed to dissipate wakefulness and promote sleep. You're not fighting your environment but using it, letting it shape your state. Dissipation isn't the enemy. Letting go, losing energy, decaying from the excited state of alertness into the ground state of sleep, that's the goal. The reservoir is here to help. Let it do its job. The quantum Mpemba effect is a quantum analog of the classical Mpemba effect, where hot water sometimes freezes faster than cold water under certain conditions. In quantum systems, a highly excited initial state can sometimes reach thermal equilibrium faster than a state closer to equilibrium, which seems paradoxical. The effect depends on the specific dynamics and the structure of the quantum state, and it's not universal but occurs in certain systems under particular conditions. The lesson is that sometimes being further from your goal makes the journey quicker, that shortcuts aren't always the fastest path, that the relationship between initial state and equilibration time is nonlinear and surprising. Maybe you're feeling far from sleep right now, your mind busy, your body restless. That's okay. Sometimes the highly excited state relaxes faster than the half-asleep state. Sometimes being fully awake and letting the process unfold naturally is quicker than fighting against half-wakefulness. Don't judge your current state. Don't worry about how far from sleep you feel. The path from here to sleep might be faster than you think, faster even than if you were already drowsy. Let quantum Mpemba surprise you. Quantum discord is a form of quantum correlation that exists even in separable, non-entangled states. It measures the difference between two ways of calculating mutual information in quantum systems, and it reveals that entanglement isn't the only kind of quantum correlation. States with zero entanglement can still have quantum discord, meaning they're quantum correlated even though not entangled. This broadens our understanding of what makes something quantum. Non-classicality is richer and more nuanced than just entanglement. There are shades of quantumness, layers of correlation, multiple ways that quantum systems can be connected and coordinated beyond classical possibilities. Your relationship with yourself, your connection between conscious and unconscious, might have quantum discord even when not fully entangled. Parts of you coordinate through quantum correlations you don't consciously access. Your body knows how to sleep even when your mind doesn't. There's discord, correlation, communication happening between levels of your being that you're not aware of. Trust that deeper coordination. Trust the quantum correlations managing your transition into rest, even when your conscious mind feels separate from the process. The quantum Otto engine is a model of a heat engine operating on quantum principles, using quantum states as the working substance. It follows a cycle analogous to the classical Otto cycle, but with quantum properties enabling efficiencies and behaviors impossible classically. You can use superposition as a resource, or entanglement between different parts of the engine. Quantum heat engines reveal that thermodynamics and information theory become deeply connected at the quantum scale. Work and heat and entropy are ultimately about information, about what you know and don't know about quantum states. Quantum engines also face quantum friction, dissipation from maintaining coherence, challenges that classical engines don't have. You're an engine too, a biological engine that takes in energy and produces work, thought, movement. Right now, you're idling, reducing output, conserving energy. Your quantum Otto cycle is shifting to a low-power mode. Thermodynamically, sleep is a cooler state, a lower energy configuration. You're allowing your engine to spin down to reduce its cycle rate, to stop doing work and just exist in a low-energy equilibrium. Engines need rest too. Even quantum engines need downtime. Let your cycles slow, let your temperatures drop, let your engine rest. Quantum error correction uses entanglement and redundancy to protect quantum information from decoherence and noise. Classical error correction is straightforward. Make copies of your data, and if one copy gets corrupted, you can recover it from the others. But the no-cloning theorem says you can't copy arbitrary quantum states, so quantum error correction has to be more clever. Instead of copying the state, you entangle it with multiple physical qubits in such a way that errors on individual qubits can be detected and corrected without measuring the actual quantum information. It's like spreading the information across a network, so that damage to any one node can be repaired using the redundancy in the network. Large-scale quantum computers will need sophisticated error correction to function reliably. Your memory works similarly, distributing information across networks of neurons so that damage to individual cells doesn't destroy memories. Your sense of self is redundantly encoded, distributed, error-corrected across your brain. And as you sleep, some of that error correction happens actively, consolidating memories, repairing neural circuits, cleaning up noise. Sleep is your brain's error correction protocol, identifying what's noise and what's signal, preserving what matters and discarding what doesn't. Let the error correction run. Let your mind do its maintenance. You don't need to supervise the process. It knows what to do. The quantum Shillard engine extracts work from a single molecule by measuring its position and using that information to operate a piston. It's a thought experiment connecting information and thermodynamics. The measurement gives you information, and information has thermodynamic value. You can convert information into work. But measurement increases entropy somewhere else in the universe, usually in the measurement apparatus or environment, so the second law of thermodynamics is preserved overall. There's no free lunch, but information is currency, a resource as real as energy. Your brain constantly extracts work from information, making decisions, forming plans, taking actions based on what you know. But acquiring that information has a cost, metabolic and entropic. During sleep, you stop acquiring new information, stop paying the cost, let the entropy balance shift. You're closing the Shillard engine for the night, no longer extracting work from measurement, allowing the system to thermally relax. There's deep wisdom in periodically stopping the information-to-work engine, in letting entropy increase without fighting it, in accepting the thermal bath's invitation to equilibrate. Tonight, you're at equilibrium with the environment, no gradients to exploit, no work to extract, just a system at rest in its thermal surroundings. Topological quantum computing uses anyons, exotic quasi-particles that exist in two-dimensional systems with special properties. When you braid the paths of anyons around each other, you perform quantum gates. The result depends only on the topology of the braiding, which paths went around which, and not on the precise details of positions or timings. This makes topological quantum computers inherently resistant to many types of errors because small perturbations don't affect the topology. You'd have to cause major disruptions to create an error. Topological quantum computing is still experimental, but it promises a robust platform for quantum computation. Topology is about global structure, about properties that don't change under continuous deformations, about what stays invariant even when details shift. Your identity has topological properties, core aspects of who you are that remain constant even as moods, thoughts, and circumstances change. Those topological features don't need protection, they're inherently stable. As you drift into sleep, the details of your thoughts will change, dissolve, become strange, but the topological you, the core structure, remains. You can't lose yourself in sleep. The braiding of your experiences, the paths of your life, those define you in ways that small perturbations can't touch. Rest in your topological stability. The quantum speed limit sets fundamental bounds on how quickly a quantum state can evolve from one configuration to another. It's related to the energy uncertainty and the time of evolution, connecting dynamics to thermodynamics and information theory. You can't change quantum states arbitrarily fast. There's a speed limit imposed by the physics. Rushed transitions violate the quantum speed limit and simply can't happen. This means patience is built into the universe at a fundamental level. Certain things simply take time, not because of practical limitations, but because reality itself has speed limits. Falling asleep is subject to its own speed limits, biological and perhaps quantum. Your brain state can't flip from waking to REM instantly. The transition requires time, the passage through stages, the gradual shift of neural patterns. Trying to force it faster than the speed limit just creates errors, frustration, wakefulness. Respect the speed limit. Let the transition take the time it takes. The universe is patient with its quantum evolutions, and you can be patient with yours. No rushing. Just the natural pace of state evolution, governed by the laws underlying everything. The quantum pigeonhole effect, already mentioned earlier in terms of the principle, extends into strange predictions about pre- and post-selected quantum systems. With careful choice of initial state and post-selection of final state, you can make measurements that seem to place 3 quantum particles in 2 boxes with no box containing more than 1 particle. The apparent paradox resolves when you consider that you're not measuring straightforward occupancy, but conditional probabilities in a pre- and post-selected ensemble. Still, it shows how quantum mechanics allows logical structures that classical reasoning can't handle. The universe isn't bound by classical logic, and neither are you, especially as you approach sleep. Dream logic is quantum logic, allowing contradictions, superpositions, impossible situations that somehow make sense within the dream. You'll be in 2 places at once, meet people who are simultaneously alive and dead, experience time flowing backwards or not at all. That's not a bug. It's quantum logic manifesting in conscious experience. Your mind is releasing classical constraints, allowing quantum possibilities to surface. Let the logic become strange. Let impossibilities coexist. That's the doorway to dreams. The GHZ state, Greenberger-Horn-Zeilinger state, is a special kind of entangled state involving three or more particles that shows even stronger violations of local realism than Bell states. With GHZ states, you can create situations where quantum mechanics and local hidden variable theories make opposite predictions with certainty, not just statistical differences. It's an even sharper demonstration of quantum non-locality. Three particles can be entangled in such a way that measuring one affects the others instantaneously, and the correlations are perfect, not probabilistic. The universe coordinates three spatially separated objects without any signal passing between them. It's like three people widely separated instantly giving the same answer to a question without communicating, and doing so reliably every time in a way no pre-agreed strategy could accomplish. The universe is coordinated in ways that transcend space and time. And maybe your body, mind, and something else, spirit, consciousness, whatever you want to call it, are in a GHZ state, entangled, coordinated without needing to communicate. Body knows what mind needs. Mind trusts body to handle breathing. Something deeper coordinates both without conscious effort. Trust that tripartite entanglement. Trust the coordination. You're GHZ entangled with yourself and with the processes of sleep. It will happen in coordination even if you can't trace the signals. The quantum walk is the quantum analog of a classical random walk, where each step is a random direction. In a quantum walk, superposition allows the walker to take multiple paths simultaneously, and interference between paths affects where the walker is likely to end up. Quantum walks spread out faster than classical random walks and show characteristic interference patterns. They're used in quantum algorithms and can model various quantum processes, including electron transport in molecules and light propagation in disordered media. Your thoughts as you drift are doing a quantum walk through memory space, concept space, association space. Each thought branches into multiple simultaneous paths, interfering with others, creating patterns of activation that feel random but have quantum structure. You're not following a linear path toward sleep but performing a quantum walk where many paths exist in superposition, and eventually one path dominates, the one leading into dreams. Don't try to control which path. Let the quantum walk explore all of them at once. Interference will select the destination. You're already walking in superposition. You're already on multiple paths. One of them leads to sleep, and quantum interference is guiding you there even as you wander through thoughts and sensations. Trust the quantum walk. It knows where it's going. Squeezed states of light have reduced quantum noise in one property at the expense of increased noise in a conjugate property, respecting the uncertainty principle while optimizing for specific measurements. Squeezing the noise in one quadrature of the electromagnetic field allows for more precise measurements in that variable. Gravitational wave detectors use squeezed light to reduce noise below the standard quantum limit, enabling the detection of astonishingly faint signals from cosmic events. Squeezing is about resource allocation, accepting noise in one area to gain precision in another. You can't eliminate quantum uncertainty, but you can shape it, direct it toward what you care about. Your attention works similarly. You can't attend to everything, but you can squeeze your attention onto specific things, accepting noise and ignorance elsewhere. Right now, you might squeeze your attention onto breath, onto body sensations, onto the cadence of these words, accepting that thoughts will be noisier, less controlled. That's okay. You're squeezing your conscious state to favor relaxation even if it means more uncertainty in mental content. The uncertainty principle allows this trade-off. Use it. Squeeze your state toward sleep. The quantum Newton's cradle is an experimental realization where a one-dimensional gas of ultra-cold atoms is set in motion and doesn't thermalize for a very long time. In a classical Newton's cradle, the balls keep bouncing in a predictable pattern, but energy gradually dissipates and it stops. In the quantum version, the system fails to reach thermal equilibrium even after thousands of collisions because integrability and quantum effects prevent thermalization. The system remembers its initial conditions far longer than you'd expect. It's pre-thermalization, a state where the system looks thermal in some respects but retains memory of how it started. Not everything thermalizes quickly. Not everything forgets. Some systems hold onto their initial coherence for remarkably long times. You might feel like you should have thermalized into sleep by now, should have forgotten the day and settled into rest, but maybe you're in a pre-thermalized state, still carrying memory of waking even as you approach sleep. That's okay. Even quantum systems can take thousands of interactions to fully thermalize. Give yourself time. The full thermal equilibrium of sleep will come. You're in the approach, the pre-thermalized state, and it's a valid part of the process. Memory will fade. Thermalization will complete, just not instantly. The quantum Lissajous states are special quantum states of two-dimensional harmonic oscillators that produce Lissajous figures, those beautiful looping patterns made by combining perpendicular oscillations. In quantum mechanics, these states have elegant mathematical structure and connections to quantum optics and molecular physics. They represent coherence, order, precise relationships between perpendicular modes of vibration. But they're also fragile, easily disturbed by decoherence. The loops collapse into statistical clouds as the environment intrudes. The beauty is temporary. The order is conditional. And there's something poignant about that, the way quantum systems can achieve exquisite structure that's inherently transient. Your waking consciousness is a quantum Lissajous state, a beautiful temporary pattern in the phase space of neurons. Sleep is the decoherence, the environment intruding, the collapse of those elegant loops into something more random. But the collapse isn't a failure, it's part of the cycle. Coherence and decoherence alternate, structure and noise trade places. You'll return to coherent Lissajous patterns when you wake. For now, let the loops dissolve. Let decoherence do its work. The pattern will form again tomorrow. Quantum state tomography is the process of reconstructing an unknown quantum state through repeated measurements on many identical copies of the state. You can't learn everything from one measurement, but by measuring different observables on an ensemble, you can reconstruct the full density matrix. It's an expensive process, requiring many copies and many measurements, but it's how researchers characterize quantum systems in labs. You're doing a kind of tomography on your own state right now, gently probing how awake you feel, how relaxed your body is, how active your thoughts are. Each little check is a measurement, collapsing part of your state, giving you information. But unlike quantum particles, you're not trying to fully characterize yourself. You're just checking in, making sure the trajectory is toward rest. Too much tomography, too much self-measurement keeps you in a collapsed state pinned by observation. Let the measurements become sparse. Check in less often. Let yourself return to sewer position between observations. The more you measure whether you're asleep, the more you collapse into definite wakefulness. Stop checking. Let the state evolve unmeasured. Tomography requires many measurements, but sleep requires none. The quantum backflow effect is a counterintuitive phenomenon where a quantum particle with positive momentum, moving to the right, can have a probability current flowing to the left. The particle is moving right, but the probability of finding it further left can increase for a brief time. It doesn't violate conservation of probability or momentum, but it shows that quantum probability currents can behave strangely, flowing opposite to the average particle motion. The wave function has structure, interference, regions where probability sloshes backward even as the overall flow is forward. Your journey toward sleep might have backflow too. You might feel more awake sometimes even as the overall current is toward sleep. Alertness might spike even as the general trend is downward. That's not failure, it's quantum backflow, a natural consequence of the interference patterns in your mental state. Don't be discouraged by moments of increased wakefulness. The overall current is still flowing toward rest. Backflow is temporary, local, a ripple in the overall trend. The momentum is toward sleep even when probability briefly flows backward. Trust the average. Trust the momentum. The backflow will pass. 3/4 of the way through now. You're deep into this journey through quantum space, and whether you remember any of it or not, it's doing its work, giving your mind something to follow, a gentle tether as consciousness drifts. Your body knows what it's doing. Every muscle is softening, every breath is slower than the one before. Let your face relax completely. There's no expression to hold, no communication to manage. Your eyes can rest behind your lids, no focus required, just the gentle darkness. These quantum facts are like photons, arriving one by one, each carrying a tiny bit of information, most of which passes right through you without leaving a trace. And that's perfect. You're translucent to these ideas now, letting them pass, barely interacting. That's how you know you're close to sleep, when words become sounds, meanings become textures, and nothing needs to stick. Keep drifting. You're doing perfectly. The quantum Darwinism concept proposes that classical reality emerges from quantum reality through a process analogous to natural selection. Quantum systems constantly interact with their environment, leaving many imprints or copies of certain information about themselves. The information that's most robustly copied into the environment becomes what we call classical, objective reality. Observer-independent facts emerge because many observers can access the redundant environmental copies. States that don't get robustly copied remain quantum, hidden, inaccessible. Reality, from this view, is the information that survives and proliferates through environmental interaction. Your memories work similarly. The experiences that get rehearsed, discussed, integrated into multiple contexts, become solid, classical parts of your history. The experiences that don't get reinforced remain quantum, fuzzy, uncertain, perhaps never quite collapsing into definite narratives. Sleep will affect which memories survive. The day's experiences are still quantum, still malleable. Tonight, some will be copied robustly into long-term memory, becoming classical facts of your history. Others will fail to proliferate and will fade. Quantum Darwinism is happening in your brain right now, selecting which experiences deserve to become part of your classical reality. You don't control the selection. Evolution handles it, quantum processes interacting with neural environment, leaving copies of what matters and letting the rest dissolve. The quantum contextuality theorem shows that the result of measuring a quantum observable depends on what other observables you measure alongside it. The value doesn't exist independently, but is contextual, depending on the full measurement context. This is true even for commuting observables that don't disturb each other. Quantum mechanics violates non-contextuality, a principle that seems obvious. A property should have a value independent of how you measure it. But no, the universe is contextual. What something is depends on the context of observation. Your experiences are contextual too. How you feel about an event depends on what other thoughts accompany it, what context surrounds it. The same memory can feel different in different mental contexts. Nothing has absolute meaning independent of its context. And in dreams, contextuality becomes extreme. Objects transform based on what else is in the dream. Identities shift with narrative context. Meaning is totally fluid and context-dependent. As you approach that dream state, you're entering a realm of maximum contextuality, where nothing has fixed properties, where everything is defined only relationally, contextually, quantum mechanically. Let your thoughts become contextual. Let their meanings shift based on what else is present. Fixed interpretations are dissolving. Context is everything now. The quantum Jarzynski equality relates the irreversible work done on a system driven out of equilibrium to the equilibrium-free energy difference. Even when processes are far from equilibrium and entropy is produced, there's a precise mathematical relationship connecting non-equilibrium work to equilibrium thermodynamics. It's a fluctuation theorem, revealing that even far from equilibrium, certain statistical regularities hold, connecting the microscopic reversibility of physics to the macroscopic irreversibility of thermodynamics. The universe keeps accounts at a deeper level than we see. Energy and entropy balance in ways that aren't obvious from the surface. Your life is a non-equilibrium process, constantly driven, never at equilibrium while awake. But the fluctuation theorems apply to you too. The work you do, the entropy you generate, connects back to equilibrium thermodynamics in precise ways. And sleep is your equilibrium reference state, the place you return to, the baseline against which waking activity is measured. Jarzynski equality says that no matter how far you've been driven from equilibrium today, there's a path back, a statistical connection to the equilibrium state. Sleep is that path. The equality guarantees that return is possible, that equilibrium can be regained. Trust the fluctuation theorem. Trust that the irreversible work of the day connects mathematically to the equilibrium of sleep. The equation holds. The return is assured. The quantum Fokker-Planck equation governs the evolution of probability distributions for open quantum systems, accounting for dissipation and diffusion from environmental coupling. It's a quantum analog of the classical Fokker-Planck equation, describing how probability density spreads and shifts over time in phase space. The equation captures both the deterministic drift and the stochastic diffusion of quantum states under environmental influence. Your conscious state is governed by something like a quantum Fokker-Planck equation, drifting under systematic influences, circadian rhythms, sleep pressure, and diffusing under stochastic influences, random thoughts, environmental noise. The drift is toward sleep as the evening progresses. The diffusion represents the noise, the unpredictability. But the equation has an attractor, a stable point where drift and diffusion balance, and that attractor is sleep. Stochastic processes with attractors always reach them eventually, given enough time. You're a stochastic process with sleep as the attractor. The diffusion might be high right now, thoughts wandering randomly, but the drift is always present, always pulling toward the attractor. Eventually, inevitably, the attractor wins. You'll arrive at sleep because the Fokker-Planck equation governing your state has sleep as its stable fixed point. The math is on your side. Drift toward it. Quantum supremacy, now often called quantum advantage, is the point where quantum computers can perform a specific task that classical computers effectively can't, not because of better algorithms, but because the quantum system natively embodies the solution. Google claimed quantum supremacy in 2019 with a chip that sampled from a probability distribution in 200 seconds that would take classical supercomputers thousands of years to simulate. The task was somewhat artificial, designed to showcase quantum advantage rather than solve a practical problem, but it demonstrated that quantum hardware has crossed a threshold. Quantum systems can do things classical systems can't, not just faster but fundamentally differently. Your quantum substrate, the actual quantum processes in your neurons and biochemistry, gives you advantages over classical computation. Consciousness might require quantum effects that classical computers can't replicate. You're a quantum computer made of meat and neurons, and you have native quantum supremacy over silicon in certain domains like contextual understanding, emotional resonance, creative leaps. As you sleep, your quantum advantage will process the day's information in ways classical computation can't match, consolidating, dreaming, integrating. Trust your quantum substrate. It's supremely good at what it does. Let the quantum computation of sleep run its course. No classical algorithm can substitute for what your brain does when it rests. The quantum scattering problem involves sending a particle toward a potential barrier or target and calculating the probability of different outcomes: transmission, reflection, absorption. The math becomes beautifully rich in quantum mechanics, with resonances where transmission probabilities peak, with tunneling allowing particles through barriers, with interference creating complex angular distributions. Scattering is how we learn about the quantum world. We scatter particles off each other and see what happens. Every particle physics experiment is a scattering experiment at heart. You've been scattering off the world all day, interacting, bouncing off situations and people, absorbing some encounters and transmitting through others. Each interaction has its quantum amplitude, its probability, its phase. Tonight, you stop scattering. You withdraw from the interaction region, remove yourself from the target area, become a free particle no longer colliding with anything. Sleep is the absence of scattering, the time when you're not bouncing off the world but propagating freely in your own mental space. No targets, no barriers, just free evolution. The scattering cross-section drops to zero. The interaction ceases. You're free. Let yourself propagate freely through the night, unscattered, undeflected, just evolving under your own Hamiltonian. The Deutsch-Jasa algorithm was one of the first quantum algorithms showing exponential speedup over classical approaches. It solves a specific problem, determining whether a function is constant or balanced, using a single query, whereas classical algorithms need multiple queries. It's not a practical problem, but it proved that quantum computers could be fundamentally more efficient for certain tasks. The algorithm uses superposition to query all possible inputs simultaneously and interference to extract global properties of the function. It's a proof of concept. Quantum parallelism is real. Interference can extract answers. Quantum advantage exists. Your own mind uses something like quantum parallelism, processing multiple possibilities simultaneously, using interference to amplify good ideas and cancel out bad ones. You don't evaluate options one at a time, but hold many in superposition and let them interfere until one emerges as the choice. In dreams, this becomes even more pronounced. Scenarios play out in parallel, and dream logic selects based on emotional resonance and associative interference. Tonight, your unconscious will run Deutsch-Jasa-like algorithms on the day's experiences, querying them in superposition, extracting global properties, determining what's meaningful and what's not. Trust the algorithm. It's been running in humans for millennia. Let the quantum query proceed. The quantum witness observable is an operator that detects entanglement without requiring full quantum state tomography. Measuring a witness can confirm that a state is entangled without reconstructing the entire density matrix, which is much more efficient. Witnesses exist for every entangled state, though finding the optimal witness for a given state is non-trivial. It's an example of how cleverness can reduce the cost of quantum measurements, how you can learn specific things without learning everything. You don't need to fully understand yourself to know that you're tired, that you're ready for sleep. There are witness observables in your own experience, heavy eyelids, yawning, drifting thoughts, that confirm the sleep state is approaching without needing to analyze every neuron. Trust the witnesses. They're reliable indicators. You don't need complete self-knowledge. The witnesses tell you what you need to know. Sleep is near. The entanglement between your circadian system and your sleep homeostasis is producing the right correlations. The witness observables are positive. Sleep is confirmed without needing further measurement. Let the witnesses be enough. They're detecting what's already true. You're entangled with sleep, and the observables prove it. The quantum Bernstein-Vazirani algorithm determines a hidden binary string with a single query, whereas classical algorithms require multiple queries. Like Deutsch-Jasa, it's a toy problem demonstrating quantum advantage through superposition and interference. The hidden string is revealed by querying all possible inputs at once, and letting quantum interference filter out everything except the answer. It's almost magical how interference selects the correct answer from exponentially many possibilities. Your memory retrieval works similarly, searching vast associative networks in parallel, using spreading activation and interference to surface the relevant memory. You're not searching serially through every memory. You're querying in superposition, and interference brings forward what matches the cue. In sleep, memory consolidation uses similar principles, integrating new information into existing networks, letting interference strengthen coherent patterns and weaken noise. The Bernstein-Vazirani algorithm is running in your hippocampus right now, processing hidden strings of daily experience, revealing their structure through quantum parallelism. The algorithm is efficient, elegant, and unconscious. You don't need to supervise it. Sleep handles the queries. Let it run. The quantum variational algorithms optimize parameters of a quantum circuit to minimize a cost function, using a classical optimizer to adjust the parameters and a quantum computer to evaluate the cost. It's a hybrid approach suitable for near-term noisy quantum computers. The quantum computer explores the solution space using superposition and entanglement, while the classical optimizer guides the search. Together, they tackle problems like finding molecular ground states or solving optimization problems. Your own learning is variational, adjusting synaptic weights to minimize prediction errors, using the quantum substrate to explore possibilities and classical-like processes to guide the search. Sleep plays a role in this optimization, allowing synaptic weights to adjust without the noise of sensory input, running the variational algorithm on a quieter substrate. Your brain is running quantum variational optimization right now, tuning itself, adjusting parameters, minimizing the cost function of being misaligned with reality. The process requires rest, requires low noise, requires the system to explore freely without constant external input. You're providing those conditions. The variational algorithm appreciates it. Let the optimization run. Tomorrow you'll wake up with slightly better parameters, slightly lower cost, slightly more aligned. The quantum optimizer needs this time. Give it space. The GKS-Lindblad master equation describes the most general form of a Markovian open quantum system's evolution, capturing how a system evolves under environmental interaction when the environment has no memory. The equation is the quantum analog of a classical master equation, tracking how the density matrix changes due to both unitary evolution and dissipation. It guarantees that the density matrix remains physical, positive, trace-preserving under all conditions. The Lindblad operators encode how the environment causes transitions, decoherence, and relaxation. Your brain is an open quantum system, constantly interacting with a biological environment, body temperature, blood flow, chemical signals. The GKS-Lindblad equation, or something like it, governs how your neural quantum states evolve and decohere. The environment causes dissipation, pushing you toward equilibrium, toward sleep. The Lindblad operators encode fatigue, circadian rhythms, homeostatic sleep pressure. The equation guarantees that your state remains physical, that you won't enter impossible configurations, and the attractor of the equation when night comes is sleep. The master equation is driving you there. You're not fighting a battle, you're flowing along the master equation's path. The environment is pulling you toward the attractor. Don't resist the dissipation. It's not loss, it's the path. Lindblad operators are guiding you home. The quantum fluctuation dissipation theorem connects the spontaneous fluctuations in a system at equilibrium to its response to external perturbations. It says that the same interactions causing dissipation also cause fluctuations, and they're balanced in equilibrium. The theorem is a cornerstone of statistical mechanics and has quantum versions that apply to quantum systems in thermal baths. It tells you that noise and response are two sides of the same coin, that the universe doesn't give you fluctuations without also giving you a way to dissipate energy, and vice versa. Your experience right now includes fluctuations, random thoughts, body sensations, spontaneous images, and those fluctuations are connected to how you respond to these words, to the room, to your own intention to sleep. The fluctuation-dissipation balance is being maintained by the thermodynamics of your neural environment. As you approach equilibrium with the thermal bath of the night, fluctuations quiet, responses dampen, and everything settles into balance. The theorem guarantees this. Fluctuation and dissipation will reach equilibrium. Noise will diminish. Response will soften. You're moving toward the balance point, the equilibrium predicted by the theorem. Trust it. The physics ensures it. Equilibrium is inevitable. Quantum criticality occurs at zero temperature phase transitions, where quantum fluctuations, rather than thermal fluctuations, drive the system between different phases. Near a quantum critical point, the system exhibits scale invariance and long-range correlations, with properties that don't depend on microscopic details, but only on symmetries and dimensionality. Quantum critical systems show emergent behavior, universality, and exotic phenomena like non-Fermi liquid behavior. Strange metals, high-temperature superconductors, and other complex materials exhibit quantum criticality, suggesting deep organizing principles we don't fully understand. Your brain might operate near a kind of critical point, poised between order and disorder, maximizing information processing and flexibility. Criticality allows rapid response, long-range communication, and adaptability. In sleep, the critical point shifts, the balance changes, and different collective behaviors emerge. You're a quantum critical system transitioning between phases, from waking to sleeping, from criticality tuned for interaction with the world to criticality tuned for internal processing. The transition is smooth, continuous, but crosses a critical threshold where qualitative changes occur. You're approaching that threshold now. The quantum fluctuations are guiding you across. On the other side is sleep, a different phase of consciousness, governed by different critical dynamics. Trust the phase transition. Criticality knows what it's doing. The quantum Grover's algorithm searches an unsorted database of n items in roughly square root n steps, a quadratic speedup over the classical linear search. It uses amplitude amplification, repeatedly applying operations that increase the amplitude of the target state while decreasing others. After the right number of iterations, measuring the quantum state gives the target with high probability. It's not exponential speedup, but it's still significant, and it applies to a wide range of search and optimization problems. Grover's algorithm shows that quantum mechanics gives a modest but real advantage in finding needles in haystacks. Your mind searches through vast conceptual spaces, and perhaps quantum processes give you a Grover-like advantage, finding relevant ideas faster than classical random search would allow. As you drift toward sleep, your mind is still searching, but the target has changed. You're searching for the off switch, the state of consciousness that ends the search itself. Grover's algorithm is running, amplifying the amplitude of restful states, decreasing the amplitude of alert states. Each iteration brings you closer. The amplitude of sleep is growing. A few more iterations and the measurement will collapse you into rest. The algorithm is working. Let it amplify. Let the iterations continue. The target is near. The quantum Zeno effect has been proposed as relevant to consciousness in some theories, where continuous observation by consciousness keeps certain neural states stable, preventing quantum transitions that would otherwise occur. It's speculative, but the idea is that attention stabilizes certain quantum configurations, collapsing them repeatedly and freezing them in place. When attention withdraws, the system can evolve quantum mechanically, exploring superpositions and transitioning between states. If true, sleep might be partly about releasing the quantum Zeno effect, allowing neural quantum states to evolve freely without the freezing influence of continuous conscious observation. Your consciousness has been collapsing your brain's quantum states all day, keeping them definite, preventing them from wandering. Now, as consciousness dims, the quantum Zeno effect weakens, and neural quantum states can breathe, can explore, can transition. This might be why dreams are so strange. They're what happens when quantum evolution proceeds without constant collapse. Let your attention weaken. Let the quantum Zeno effect fade. Let your neural states decohere from the classical configuration that attention enforces and recohere into dream configurations, quantum superpositions that waking consciousness would never allow. Stop watching. Stop collapsing. Let the quantum states evolve freely. The quantum time crystals are states of matter that exhibit periodic structure in time, analogous to how ordinary crystals have periodic structure in space. A time crystal spontaneously breaks time translation symmetry, oscillating between states even in its ground state, without consuming energy. They're strange objects that seem to violate intuitions about equilibrium, though they don't violate thermodynamics when properly understood. Time crystals have been experimentally realized in chains of ions and other systems, demonstrating that temporal periodicity can emerge as a robust, stable phase of matter. Your biological rhythms, circadian, ultradian sleep cycles, might have aspects of time crystallinity, periodic structures maintained by quantum effects at some level. Your heartbeat, your breath, your brain waves, all have temporal periodicity that seems almost crystalline in its stability. Tonight you're transitioning to the periodic structure of sleep, a different temporal crystal, a rhythm of REM and non-REM cycles repeating through the night. You're entering the time crystal of sleep, where consciousness oscillates through stages in a stable, predictable pattern. The crystal is forming now, the periodicity establishing itself. Let the temporal structure take over. Let the time crystal's rhythm guide you. Periodicity will emerge. The crystal will form. You'll cycle through its states automatically. The quantum Aharonov-Anandan phase is a geometric phase that accumulates when a quantum state is cycled through a sequence of changes, generalizing the earlier Berry phase. Even if the Hamiltonian varies in time, even if the cycle isn't adiabatic, geometric phases accumulate, depending only on the geometry of the path in state space, not on timing or dynamics. These phases are robust, topological, revealing deep geometric structure in quantum mechanics. Your daily cycle, waking to sleeping to waking again, is a cycle through consciousness state space, and perhaps geometric phases accumulate, phases that depend on the journey's shape rather than its duration. How you transition through the day affects what phase you arrive at in sleep, and that phase affects how you transition into the next day. It's not just about time spent or energy expended, but about the geometric path through consciousness space. The Aharonov-Anandan phase is accumulating as you drift. The path you're taking through waking down states is tracing a geometry in consciousness space, and that geometry will affect the phase you enter sleep with. The phases are inevitable, geometric, depending on the curve you trace. Trust the path. The geometry is being drawn. The phase is accumulating. By morning, you'll have completed a cycle, accumulated a full geometric phase, and returned to waking transformed by the journey's topology. The quantum marginal problem asks which sets of marginal probability distributions for subsystems are consistent with some global quantum state. Given the reduced density matrices for parts of a multipartite system, does there exist a global state that reduces to those marginals? It turns out to be a difficult problem, related to representation theory and computational complexity. Not all sets of marginals are consistent with a quantum state, and determining consistency is hard. This problem connects to questions about how local information constrains global states, about emergence and reduction, about whether the whole is determined by its parts. Your experience is a marginal problem too. Your sensory experiences, emotional states, thoughts are all subsystems, marginals of some global state of your brain or body or self. Are they consistent? Is there a global you that reduces to these local experiences, or are the marginals incompatible, fighting each other, creating tension? In sleep, the marginal problem relaxes. The subsystems stop demanding consistency. Dreams are marginally inconsistent, impossible combinations of local states that no coherent global state could produce, yet they happen anyway because the enforcement mechanism is off. Let your marginals become inconsistent. Let your thoughts, feelings, and sensations stop needing to add up to a coherent whole. The quantum marginal problem allows impossible combinations when you stop checking. Consistency is optional in dreams. The quantum anharmonic oscillator adds nonlinear terms to the harmonic oscillator potential, creating a system that's more realistic for modeling actual molecular vibrations in field theories. Anharmonicity breaks the evenly spaced energy levels of the harmonic case, creating complicated spectra and dynamics. It makes the system richer, more difficult to solve, but also more interesting and more applicable to real physics. Perturbation theory, numerical methods, and approximate techniques are needed to handle anharmonicity. Your life is anharmonic too, not a perfect harmonic oscillator with predictable, evenly spaced energy levels, but a messy, nonlinear system with irregularities and surprises. Sleep doesn't come in evenly spaced cycles. Your energy doesn't decrease linearly. There are anharmonic terms, frustrations, sudden shifts, but those anharmonicities are what make you real, not a toy model. The anharmonicity is what gives you character, complexity, humanity, and techniques exist to handle anharmonic systems, perturbative approaches that work even when the problem isn't exactly solvable. You're using those techniques right now, perturbatively approaching sleep, making small corrections, adjusting, compensating for the anharmonic terms. The approach converges. The anharmonicity is manageable. Sleep is a stable attractor even in the anharmonic system of your consciousness. Let the nonlinear terms be there. They make the solution richer. The quantum no-deleting theorem complements the no-cloning theorem, stating that you can't delete an unknown quantum state from one system without leaving a trace elsewhere. Just as you can't copy quantum information perfectly, you can't erase it perfectly. Information is conserved in a deep sense in quantum mechanics. Whatever happens to a quantum state, the information persists somewhere in the universe, possibly in correlations with the environment, possibly in entangled partners. You can't make information disappear without a trace. Your experiences today can't be perfectly deleted. Even if you forget them consciously, they've left traces in your neural network, in your body, in the environment you interacted with. The information has spread out, become encoded in subtle correlations, perhaps inaccessible but not destroyed. Sleep doesn't delete the day. It transforms it, consolidates some parts, deprioritizes others, spreads the information into long-term storage and environmental correlations. The no-deleting theorem applies to your memories. They can't vanish without a trace, so don't try to delete them. Let them be transformed, integrated, spread out into the quantum correlations of your neural network. The information will persist in some form. The theorem guarantees it. Let the transformation happen naturally. Deletion is impossible, but transformation is inevitable. The quantum thermodynamic uncertainty relations set limits on the precision of currents and fluxes in non-equilibrium systems relative to the entropy produced. Achieving high precision in a thermodynamic current requires generating significant entropy, consuming resources. There's a trade-off between accuracy and efficiency at the thermodynamic level. These relations apply to molecular motors, biochemical networks, and any system operating away from equilibrium. Your body operates far from equilibrium, maintaining precision in heartbeat, temperature, metabolism, and it pays for that precision with entropy production, with energy consumption. During sleep, precision demands relax. Heart rate variability increases, temperature drops, metabolic precision loosens. You're allowing thermodynamic uncertainty to increase, reducing entropy production, conserving resources. The uncertainty relations allow this trade-off. Less precision, less entropy, more rest. You don't need precision right now. You can be uncertain, variable, imprecise. The thermodynamic cost drops as precision requirements relax. Let yourself be uncertain. Let the currents fluctuate. The entropy production decreases, and that's restful. Uncertainty is low cost. Embrace it. Let thermodynamics guide you to low energy, high uncertainty rest. And here we are, at the end of our 100 quantum facts, at the edge of sleep and waking, in the superposition between thought and dream. The quantum world has walked with us through this long night, revealing layer after layer of strangeness and beauty, of uncertainty and connection, of particles that are waves and measurements that create reality and entanglements that transcend space. You've journeyed through superposition and tunneling, through Bell's theorem and Heisenberg's uncertainty, through virtual particles bubbling in the vacuum and geometric phases accumulating in cycles. You've seen that the universe, at its smallest scales, is far stranger and more wonderful than our everyday experience suggests, and yet it's the foundation of everything we are and everything we experience. You are made of quantum fields, sustained by quantum tunneling, connected through quantum correlations that you can't see but that shape every moment. And tonight, you've let those quantum processes guide you toward rest, toward sleep, toward the ground state of consciousness where restoration happens, where memories consolidate, where dreams arise from the quantum foam of neural activity. The universe is taking care of itself at every scale, from Planck length to cosmic horizon, and you're part of that self-care, that universal tendency toward equilibrium, toward order emerging from chaos, toward rest following activity. Sleep is written into the laws of physics as surely as gravity and light. So let go completely now. Let the quantum world carry you. Let the wave function collapse into dreams. You've reached the end of our journey together, but your journey through the night continues. Thank you for being here, for listening, for letting these strange and beautiful ideas accompany you toward rest. May your dreams be full of superpositions, and your rest be as deep as the quantum vacuum. Good night. And so we've traveled together through 100 quantum facts, through the strange territory where particles are also waves, where observation creates reality, where entanglement connects across space, and where uncertainty is built into the fabric of existence. The quantum world has been our companion tonight, offering its paradoxes and beauties, its unsolved mysteries and its precisely tested truths. If you're still awake, that's perfectly okay. Sleep will come when it comes in its own time, according to its own quantum probabilities. There's no right or wrong here, no success or failure, only the gentle process of allowing transition, of moving from one state to another in whatever time the universe requires. The quantum world teaches us patience, teaches us that some things can't be forced or rushed, that observation changes what we observe, that letting go of the need to know allows possibilities to exist in superposition until the moment requires a choice. You've been practicing that all night, letting these ideas wash over you without needing to grasp them, existing in a superposition of understanding and not understanding, letting meaning remain uncertain and that being okay. Perhaps that's the real lesson quantum mechanics offers to those of us lying in the dark seeking rest. That uncertainty is not a problem to be solved, but a feature of reality to be accepted. That connection exists beneath the surface even when we feel alone, that the smallest things contain infinite depth, and that there's a kind of peace in acknowledging how much we don't and can't know. Thank you for spending this time here, for letting these quantum thoughts be your companions as the night deepens. Whether you've understood every fact or simply let the words become a soft rhythm, Whether you're already dreaming or still awake and listening, you've given yourself this gift of time, of rest, of stepping back from the day's demands and letting yourself simply be a quantum system in a thermal bath, drifting toward equilibrium. If you found this helpful, if these sleepy science explorations bring you peace, consider subscribing to find more journeys like this one. But there's no obligation, no expectation. You're free to return or not, to remember this or forget it, to let it all dissolve into the quantum foam of memory where everything is stored but not always accessible. As we close, let yourself sink just a little deeper. Let whatever tension remains drain away like probability amplitude spreading through space. Your breathing is slow and natural. Your body is heavy and supported. Your mind is quiet or active, and both are fine. The quantum world continues its mysterious dance whether you're awake to witness it or not, and you're part of that dance, a beautiful temporary pattern in the universal wave function. Sleep well, rest deeply, and may the quantum universe hold you gently through the night. The sleepy science place will be here whenever you need it, but for now, there's nothing left to do but let go, release, and drift. Thank you for being here. Good night and sweet dreams in the quantum realm where everything is possible and nothing is certain, where you're free to be anything, go anywhere and rest completely. Good night.